Okay. Okay, so it's my big pleasure to introduce Izzet Coskun from Chicago, who will speak about the stabilization of cohomology of moduli space of sheaves.
Well, thank you very much, and thanks for being here. There were some just the possibility that maybe the slides are not showing so well. They are also on my website, so you can get them from what I put on the chat if you want to follow it along from there. So anyway, everything that I'm going to talk about today is joint work with Matthew Wolf. So let me just maybe start with the background. So we'll work on a smooth, irreducible, complex projective surface, and H will be an ample divisor on X. And all the sheaves here that we talk about will be coherent and torsion free unless I explicitly say so. So let me briefly recall what we mean by a stable sheaf. So what you can do is if you have your ample H and you have your sheaf, then you have the Hilbert polynomial associated to it. Since we are on a surface, it's a polynomial of degree 2. And so it starts with a2m squared over 2 plus lower order terms. And the reduced Hilbert polynomial is just defined by dividing the Hilbert polynomial by this initial coefficient a2. It's a normalization. And the way you should think about it in this case is actually the rank of the sheaf. And then, we'll talk about the slope, the discriminant. So let me give you the formula. It doesn't matter too much what these precise formulae are, but so that you just see them one time. So the slope is the first Chern class divided by the rank. The H slope is, if you dot the first Chern class by H and divide it by the rank, sometimes you normalize it by also dividing it by H squared. And the discriminant is this invariant. And the thing that's nice about the slope and the discriminant is that they work well with respect to tensor products. It's just another way of recording the Chern classes or the Chern character, but it is additive under tensor products. So that's why it's nice to have these. All right, so then the main definition that we have is that a sheaf is called Gieseker H semi-stable if for every proper subsheaf, the reduced Hilbert polynomial is less than or equal to the reduced Hilbert polynomial of this F. And what does it mean for a polynomial to be less than or equal to? It just means that that happens for M sufficiently large. And then if you have a sheaf like that, you call it Gieseker H semi-stable. And this will come up, so let me also say it, and then you call a sheaf slope semi-stable, mu H semi-stable, or H slope semi-stable, if every proper subsheaf of smaller rank has slope less than or equal to, and I should say that if the inequalities here are strict for every subsheaf, then you call it stable. Okay? And, as usual, what there is here is that, this allows you to decompose every sheaf into semi-stable parts in that there is a Harder Simhan filtration. So if you have any sheaf like this, there's some filtration such that the quotients are semi-stable with decreasing invariance. And just to and if you have a semi-stable sheaf, you also have a Jordan-Hölder filtration that splits it into stable pieces. This filtration is not unique, but the associated graded object is unique. And then if two semi-stable sheaves have the same Jordan-Hölder factors, you call them S equivalent. Okay. So now, so the nice thing about these is that if you have moduli spaces, you have projective moduli spaces parameterizing S equivalence classes of Gieseker H semi-stable sheaves with the fixed Chern character. These were constructed by Gieseker and Maruyama. And here I'm talking about surfaces, but these also exist in some higher dimension. They exist for higher dimensional varieties as well, but I'll only be talking about the case when X is a surface. And then the natural questions that arise when you have this modulus spaces, when are they non-empty? When are they irreducible? What's their dimension? And the types of answers that we have to these kinds of questions come in two forms. We know this for sort of asymptotically. Like, for instance, like, there's the Bogomolov inequality in terms of the discriminant that I put up. It says that if you have a semi-stable sheaf, then the discriminant has to be non-negative. So that's some restriction on when this moduli space is non-empty. And then there are theorems that I will talk about more that says that if the discriminant gets really large, then they become irreducible, and we know the dimensions of these spaces. And then the other types of results that we have are for special surfaces. Like if you have a K3 surface, then we understand these moduli spaces, or if you have P2, we understand these moduli spaces, and so on and so forth. But in general, these questions are wide open. But so the question that I want to concentrate on today is that what is the topology of the space? What are the Betty numbers? What does the topology of the space look like? Okay, so, but this is one of many questions that we have about these spaces. All right, so as usual, maybe to begin, let me start with the rank 1 case where we know what happens. So I'll denote by xn the Hilbert scheme of n points on x. Okay, this is a nice, smooth, irreducible projective variety of dimension 2n. And then the key point here is that if you have if you have a sheaf of rank 1, right, then it's automatically stable, and it's of the form a line bundle time the ideal tensor and ideal sheaf of points. So in some sense, if you want to understand the rank 1 case, you just need to understand this Hilbert scheme of n points. And then in that case, the topology was computed around the 80s. So it started with, I believe, Ellingsrud and Strome, who computed the Betty numbers for P2n. Then Gottsche in general computed the Betty numbers for any surface. And I'll tell you the formula in a second. But maybe before we do that, in the case of P2, you can be fairly concrete about this thing. So for instance, a basis for the cohomology was given by Berenia and Sol. So let me sort of briefly tell you what that basis looks like so that you can get a sense of what it looks like. So here, the basis for the cohomology depends on 3 partitions. So you'll have 3 partitions. The sum of the parts will add up to n, which is the n from the, let me see.
Is it just Belenitsky-Berula?
I mean, initially it was like what Ellingsrud and Strome did, but this is a little bit different. It's a more Schubert basis type thing. So let me tell you this one, because it's nice to draw the pictures. So each basis element will have 3 types of things. So here instead of saying it in general, I'll just give you an example and you'll see what happens. So here is the partition 2, 2, 3, the partition 1, 2, 2, and the partition 1, 2, 2. So what you do is you fix some number of fixed general lines. So in this case, my partition has 3 parts, so I fix 3 general lines. And then on each line, I have some number of points varying, and the number of points varying is determined by the parts. So you fix one line and you have 2 varying points on the line. You fix another line and you have 2 other varying points on the line, and you have, another line, and there you have 3 varying points. Now the second set of partitions is very similar. You have again, in this case, 3 lines, but the number of parts, the number of lines is the number of parts. And what's different here is that on each line you fix a point, and then the remaining points are allowed to vary. So here my part is 1, so I just have my 1 fixed point on that fixed line. Here my part is 2, so I have 1 fixed point and 1 moving point. And here my part is 2 again, so I have 1 fixed point and 1 moving point. And then the third type of partition is now you fix a point. This point, this denoted by star here, is not part of the scheme. But what you do is that now you ask that 1 point be collinear with that point. Here, 2 points are collinear with that point, and 2 points are collinear with that point. So here, if you have a part, that's the number of points that are collinear with that point. Of course, to say that just 1 point is collinear with respect that point is no condition. And similarly here, if I have just 1, that just means that you have 1 fixed point. Okay? And then the theorem is that, yeah.
I'm sorry. This is about which particular Hilbert scheme? I'm just completely confused.
The Hilbert scheme is you count the number of points you have. So it's the sum of the partitions. So 4, 7, 10, 12, 13, 14, 15, 17, maybe. 5 plus 5 plus 7.
So,
Right? That's the number of points I have.
so you fix three partitions, but you represent them differently, right?
That's right. Each partition has a different piece, corresponds to a different piece. And then the theorem is that as you vary over all such partitions, if you look at the closure of stuff like this, then they give you a basis of the cohomology. Okay? So just to see what are they in codimension 1? Well, if you want to have codimension 1, what you do is you just fix either one point on the fixed line. You either have a varying point on the fixed line and every other point is free. So I'm not recording the free points. Again, how do you get free points? If you look at your third type of thing, if you have 1, 1, 1, 1, 1, 1, 1, 1, 1, right? So those are all the free points. So I'm not going to record the free points. I'll just record the constraints. So you can constrain one of the points to lie on a line or 2 points to be collinear with respect to your fixed point. And if you wanted to find the codimension 2 ones, well, you could fix a point. You could ask the 2 points vary on a fixed line. You could ask that 1 point each vary on 2 fixed lines. Or you could ask the 1 point vary on a fixed line or 2 points be collinear with respect to a fixed point. You could ask the 3 points be collinear with respect to a fixed point, or you could ask that 2 pairs of points be collinear with respect to a fixed point. Okay? And now the thing that you should get out of this is that clearly the Betty number stabilizes. You see, if I wanted to make codimension 1 classes, I need to have at least 2 points before they stabilize, but you see that the second Betty number is just 2. Right? Now, if you want to make codimension 2 classes, you see if I have just 1 point, I can make the first one. If I have 2 points, I can make the first 3. And if I have 3 points, I can make the first 5. And once I have 4 points, then I can make all classes. And once you have 4 points or more, then this fourth Betty number stabilizes and there are 6. The fourth Betty number is 6. And then, you can think a little bit for yourself and convince yourself that any Betty number will stabilize once you have enough points. Okay?
Did you explain what is the codimension of a partition?
Sure, I can tell you what the codimension is, right? Like the codimension of each of the fixed, yeah, I mean, you can compute it. That's not hard, right? So constraining at the point to a line is codimension 1 condition. So the sum of these things is the codimension in this case. You subtract 1 from these numbers and you subtract 1 from these numbers and add 2 for each of the lines you have, and that will be the codimension, right? So to fix the point is 2 conditions, right? And to restrict a point to a line is 1 condition. And to say that, having 1 point be collinear with respect to a fixed point is no condition, but every other point that you put on that line is 1 condition, right? Is that okay? Sasha, was that fine?
Not really for me. I mean,
not really. Okay,
I'm completely confused by this description. But maybe that's my problem.
Okay, so maybe we'll talk about it later. Okay. But anyway, the thing that I want you to get out of this is that the Betty numbers of the Hilbert scheme stabilize. And let's see that actually happens more generally. So let me give you Gottsche's formula for the Hilbert scheme, for the Betty numbers of the Hilbert schemes of points. And so let's start with the Macdonald's formula. And Macdonald's formula is an expression for the symmetric product, first of all. So if you take the symmetric product and you write the Poincaré polynomial, so what this is that you do bit to the I, so the ith Betty number of the symmetric product, t to the I, and then, you know, we are varying this over all the different numbers of points, so that you sum by a second variable and you form this generating function. And McDonald computed what that was, and here is the formula for it, where these are the Betti numbers of your surface, B1x, B3x, and B2x. Of course, there's B0x here and B4x here, but because I assumed that the surface was irreducible, then those are just one. And this is called the zeta function of x, okay? And so this is McDonald's formula for the, you know, from this you can discover the Betti number of the n-symmetric product. You know, say you want to find the 15th Betti number on this 20th symmetric product, then you have to look at T15Q to the 20th in this expression. Okay, and then Gottsche's formula is can be expressed in terms of the zeta functions, and what you do here now, take the Poincare polynomial of the Hilbert scheme, and again sum it over all the points, and he says that it's this infinite product of zeta functions. Okay, and again, the thing that you should get out of this formula is maybe two things. One is that you can compute what it does, and the second is that actually the Betti numbers stabilize. Okay. You know, the Betti numbers of the Hilbert scheme and more generally the moduli space of rank 1 sheaves stabilize as long as the number of points or the discriminant tends to infinity. Okay, and you know, the way you can see, I mean, maybe briefly let me tell you, if you want to tell that, you know, when you have such a crazy power series, how do you tell that the numbers stabilize? What you do is you multiply this thing by 1 minus q, and you look at the coefficient of ti. If what you get is a polynomial, or more generally a Laurent polynomial in q, then that means that the Betti numbers are stabilizing, and that's an if and only if. Okay, and you know, if we go back to our
how can it be how can it be Laurent polynomial?
In this case, it's a polynomial, but more generally, it will be a Laurent polynomial once we start putting some negative powers. Okay.
Okay.
All right. I mean, in contrast, we don't know the Betti numbers of high-rank moduli spaces. I mean, I think we know it in very few cases. Okay. So that's sort of the summary for the rank 1 case, and now I want to sort of move to the higher rank case. So maybe I should stop, and are there any questions?
Not as far as I see, there's no question in the chat.
Okay, so let me maybe...
Is there a formula for the BI stab X?
Is there a formula for BI stab X? Yes, there is. And I'll tell you in a second.
Can I also ask you about this basis?
Maybe let me tell you what this formula for BI stab X is. It comes from here. Maybe I should have said this. What you do is you look at 1 minus QF QT, and you set Q equal to 1. If you set Q equal to 1, then those are the stable Betti numbers.
Can I ask you about the basis in the cohomology? Is it multiplicative?
Is it multiplicative? What do you mean by that? You mean that, like, if I multiply two such things, then you can express it as a linear combination with the next ones?
No. The question, is it precisely one other basis element with some multiplicity?
No. It's pretty complicated.
And are the structure constants known?
No, not as far as I know. I mean, yes and no. I mean, you know, there are other descriptions of the cohomology ring coming from Nakajima's work. And then in some sense, the structure constants are known. But, you know.
But is it the same basis as Nakajima uses?
No. Okay. All right, so let me tell you what the conjecture is now, okay? So fix a rank and the first Chern character, C. So I fix C1 and the rank. Then the claim is that the ith Betti number of these moduli spaces should stabilize as the discriminant tends to infinity. And furthermore, so you see these spaces, right, depend on the rank, the first Chern class, they depend certainly on the second Chern class or the discriminant, and they depend on the polarization, right? As you change the polarization, these moduli spaces are typically not the same. You know, there's a well-developed story of what kind of birational transformations happen and so on and so forth, but they are not the same in general. But the claim is that the ith Betti number is independent of R, C, and H, provided that this delta is large enough. Okay, so again, sort of, what we observe for the rank 1 case should happen in higher rank, and moreover, the stable Betti numbers should not depend on the rank. And I think that's probably the most interesting part of that statement. And you can be more precise about this thing. You can say, given an integer k, there exists some discriminant such that as long as you're bigger than that discriminant, then this moduli space is the same as the stable Betti numbers that you get for the rank 1 case. And you can say that, you can choose this thing uniformly depending on some compact subset in the ample cone and not independently of age or things like this, okay? But anyway, these things get harder to remember. The thing that maybe you should remember is that what we want to say is that these Betti numbers stabilize, and the stable Betti numbers basically don't depend on anything but the surface.
Is this conjecture known for curves?
I mean, okay, so yeah, well, I mean, this conjecture as stated doesn't make much sense for curves because, there is no second Chern class for curves, but there is a similar thing for curves, and that is that
But I mean, independence of R and C makes sense, right?
Independence of R and C makes sense. Well, I mean, for curves, right, what you can do is that you can let the rank tend to infinity. You fix the degree and you let the rank tend to infinity, then the Betti number stabilizes.
Okay.
Okay, I mean, why don't I'll say maybe a little bit more about that in a second. Okay, so then I don't know, there are 3 things that I should do. One is I should give you the evidence, one is I should make some remarks about the conjecture, and one is I should tell you like the history of it. And no matter in which order I do, people always want to know about the one that I haven't started with. So maybe let me try to say a few things about the numerology, then tell you a little bit about the history, then make some remarks, and then tell you what we can do, okay? And then I'll pause at certain times and maybe ask for questions. All right, so the first thing is let's do some numerology just with P2, okay? So here is Ellingsrud-Ström's table for Betti numbers of P2n, okay? And we saw some of these things already. So here I'm recording how many points you have. This is P2, 2 points in P2, 3 points in P2, and so on and so forth. And these are the Betti numbers. The Betti numbers, whoa, what's going on? Why is it? I'm sorry. Let me see. I see that what's being shown on my Zoom is different than what I'm seeing on my screen. So let me just do this. Okay, that's better. Okay, so these are the Betti numbers, and only half of them are written because, I mean, these are smooth, so it's symmetric. So for instance, P2 is 1, 1, 1, and so on and so forth. But you can see what happens. We said that, in codimension 1, there are 2, right? So you see the 2 happening. In codimension, I shouldn't use my cursor. In codimension, the 4th Betti number, we saw that, once you got 4 points, you got 6, and it was always 6. then you see that it becomes 13 and 29 and 57 and so on and so forth, right? So this is we already know that they have to stabilize, and we saw a few of them by just counting, and you see that they stabilize. So the next table is you're still on P2. The rank is now 2, and the first Chern class is H. Okay, so these are rank 2 bundle with first Chern class H, and this comes from Yoshioka's table. And then you see that, again, the B2 is 2, B4 becomes 6, B6 becomes 13, and 29, 57, 113, and so on and so forth. Okay. And then finally, let me give you one more, and this comes from Manshot's paper for rank 3. C1 is H, and you're still on P2. And then again, you see that B2 becomes 2, B4 becomes 6, B6 becomes 13, and so on and so forth. Okay? So this is some numerology that there are some cases where people have computed, and you see this stabilization. And the way we started this project was, Rahul Pandarapande had asked us a question, and we were just looking at the tables to see what is known. And we looked at the tables, and we were like, it's surprising that people haven't made this a conjecture before. And we started thinking about it. So it started actually by looking at these tables. So now let's see what else is known. So the conjecture is actually known for K3 surfaces and abelian surfaces. So at least for smooth moduli spaces of sheaves on K3 and abelian surfaces. So maybe let me briefly explain that. And in fact, as usual, the easiest moduli spaces are, the K3 surfaces and the abelian surfaces. They have a lot more structure, right? So, and that's really what happens in this case. And in this case, you don't even have to take any limits or anything. So, by results of Mukai, Hoybrechts, and Yoshioka, right? Smooth moduli spaces of sheaves on the K3 surface, they are hyperkähler manifolds, and they are deformations of the Hilbert scheme. So in particular, they're diffeomorphic to it. So the, the Bethe numbers are all the same. You don't have to take any limits to make the discriminants tend to infinity or anything like that. So that the stabilization in that case is just a stabilization in the case of the Hilbert scheme. And similarly, there's a similar story for abelian surfaces. There are results of Yoshioka that say that smooth moduli spaces of sheaves are essentially a Hilbert scheme of points. I mean, it's not quite, you have to modify it a little bit, but in very predictable ways. Okay, so in that case, also there is no need to take limits. The Bethe numbers are the same as the rank 1 case. You can see already. Yeah.
Is this also true when they are not fine moduli spaces?
Yeah, that I don't know actually. I think I'm not so certain about that case. So that is one of the things that I think. Yeah, I don't know the answer to that question.
I mean, I think there are examples when moduli spaces are smooth but not fine.
In that case,
I mean, when there is no universal family, but there is only quasi-universal family, when there is some Brouwer class attached.
Maybe I should be careful and say fine moduli spaces here.
Okay.
Okay. And then let me do a little bit of the history. So, this follows from the philosophy of Donaldson, Junlia, and Gieseker. So the way you should think about it is that these moduli spaces don't need to be well behaved. They can have lots of components, they can be fairly singular, they can be non-reduced and all sorts of things, right? But, the expectation is that as the discriminant tends to infinity, or the second Chern class tends to infinity, then the moduli spaces are much better behaved. And then there are various theorems of Donaldson, Junlia, and Gieseker, and maybe, put nicely in theorem of O'Grady that says that as you let the discriminant tend to infinity, the moduli space becomes irreducible. We know its dimension, we know, so things become much better, okay? So it certainly fits in that philosophy. And Jun Lee showed actually the stabilization of the first and second Betty numbers in rank 2. And I should say, actually, O'Grady in his theorem, in his paper, like says that, this theorem about the irreducibility says that the 0th Betty number becomes 1. He asks whether the, the higher Betty numbers also stabilize. And, I think certainly in the 90s, there was a lot of work about thinking about the stabilization of these numbers. The other thing that I should say is that this conjecture is actually quite similar in some aspects to this Atiyah-Jones conjecture in gauge theory and the work of taus. So what this conjecture, originally it was a conjecture for bundles on S4, and it sort of predicts what the homotopy type and the cohomology of these moduli spaces are. And then this was later generalized to basically any four manifolds, so in particular to smooth projective surfaces. And, there are similarities. And I mean, sort of formally the conjectures look the same. And then more explicitly, as I said, Yoshioka computed the Betty numbers of moduli spaces of rank 2 sheaves on P2, and he proved the stabilization to Betty numbers. Then Yoshioka and Gottsche did the Betty and Hodge numbers when the rank is 2 and X is a ruled surface. Yoshioka observed the stabilization for rank 2 bundles on ruled surfaces, and Gottsche observed that low degree Hodge numbers are independent of the ample and gave nice formulas for them. And I guess Manshot, building on the work of Moscow, gave a formula for the Betty numbers of the moduli spaces when X is P2. Though, I mean, it's a little bit hard to see from the actual formulas that the numbers stabilize in some cases. I mean, some of these formulas are not so easy to manipulate. I think that's maybe my brief history of this. So now let me make some remarks, and maybe then people can ask some questions. So the first thing is that, I stated the conjecture for the Betty numbers, but you could just as well make a conjecture for the Hodge numbers. You can say that Gottsche and Sergel computed the Hodge numbers of the rank in the rank 1 case, and they stabilize. So you can say that the Hodge numbers should stabilize in the rank R case and stabilize to whatever the rank 1 case stabilizes, at least if the moduli space is smooth. There are certain related spaces where a similar conjecture should hold. There are Matsuki-Wentworth moduli spaces with twisted Giesecker semi-stable sheaves, pure one-dimensional moduli space of pure one-dimensional sheaves, and certain Bridgeland moduli spaces, and then you expect that similar stabilizations hold. And in some cases, this is known. Like, for instance, if you look at K3 surfaces and you look at the Bridgeland moduli spaces, as long as you assume that you are away from the walls and things like this, and certain things are generic, again, they become deformation equivalent to the Hilbert scheme of points, so that, there the stabilization also holds. Like the other thing that you can ask for so far, this was just a statement that there exists an effective constant, but you can ask for effective bounds on the constant. And I had a student, for example, who worked out that effective bound for the case of P2. So you can ask for, how large does the discriminant have to be before things stabilize, okay? But so far, this just sounds like an equality of numbers, and you can ask for what's the geometric reason for the equality of numbers. So let me sort of suggest where we are going to go. This is not the only way you can go, but this is one way you can go. So what I want to do is take the Grothendieck ring of varieties, and what you do is you invert the class of A1, and then there is a natural filtration on this that you use to complete the resulting ring width. So what's this filtration? So, you say that the class of a variety times this L to the A is in the ith piece of this filtration if the dimension of X plus A is less than or equal to minus I. The way you should think about this is think of putting negative powers here. So that's the kind of game that we're going to play. And you complete the ring and we will call the resulting ring A minus. This is sometimes called the ring M, but it gets very confusing when you call it M and you have moduli spaces floating around. So we'll just call it A minus. And you say that the sequence of elements in the string stabilizes to an element A if the sequence L minus the dimension of AI times AI converges to this A in this ring, okay? All right, so given that, what you can do is the following thing. So remember, what we want to know is we want to understand the Poincare polynomials and maybe more generally the Hodge polynomials, right? So what you do, if you are given a set of projective varieties xi of dimension di, we sort of, the reason why you have this notion is that you want to have a notion that guarantees that the low degree Betti numbers stabilize. So now, like, if you're looking at L minus di xi, so by Poincare duality, there is a relation between p xi, like the Poincare polynomial for xi, and the Poincare polynomial of L minus di xi, right?
What is di?
Di is the dimension of xi. I mean, so it's, this is just the expression of Poincare duality. And then similarly, you have the Hodge, the expression for the Hodge numbers, right? And then the point here is that if these numbers really converges in this A minus, then the low Betti and Hodge numbers stabilize. This is just some bookkeeping in this ring that sort of, tells you when these numbers stabilize, okay? So now you can ask, so Ravi Vakil and Melanie Wood conjecture that actually the classes of these moduli spaces in rank 1 stabilize in this ring. So I don't know whether, to believe this conjecture or not, but, assuming that you believe this conjecture, then you can ask whether the same thing happens for higher rank moduli spaces, right? You can ask whether the classes of these moduli spaces will also stabilize to A minus, and whether they stabilize to the same thing as the rank 1 thing stabilized to. Okay? I mean, so maybe I should make a remark that in the case of rational surfaces, this conjecture is known, but I believe even for things like K3 surfaces, this conjecture is not known. And then there are some problems that before you invert some of these things and complete, like if you try to make the conjecture sort of before you go to this full ring, then it's not actually, there were some conjectures about rationality of certain functions that are actually not rational unless you invert and complete things. So it's, I'm not sure how much evidence we have for this conjecture. But anyway, if you believe that more generally, you can ask whether these rank R moduli spaces also stabilize in this ring. All right. So I told you like some remarks and some history, but once you make a conjecture, you should also be a little bit cautious about it, and then give you some caveats that perhaps a more cautious conjecture would be to replace the Betti numbers with virtual Betti numbers. Part of the trouble here is that our evidence for this conjecture, in case the moduli spaces are singular, are not so good. But the way you can, part of the speculation, if you want, is that as the discriminant increases, the cohomology becomes pure and Poincare duality holds in larger and larger ranges. I mean, we do know that the codimension of the singular locus grows, but I'm not sure that we have so much evidence for this. The other thing that I should caution you against is that we have little evidence for the conjecture for general type surfaces. I guess like there's the connection to the Atiyah-Jones conjecture type stuff and results of Jun Ni, but other than that, you know, we don't know the conjecture for general type surfaces. And then, you know, let me just point out that the geometry of these moduli spaces can be pretty terrible when delta is small. So for instance, even if you look at rank 2 sheaves on surfaces in P3, basically like these things can have arbitrarily large number of components, for instance. Like the precise theorem is something like this. If you fix any integer, then you can make the degree sufficiently large that if the degree is larger than this given number, then the moduli space of, there exists a certain second Chern class such that the moduli space of rank 2 sheaves on the surface of degree at least this dk has at least k components. And in fact, like for small discriminants, these moduli spaces can probably be arbitrarily singular and terrible. We don't have, you know, that's not the theorem, but you know, it wouldn't surprise me if that's the case. So you really need to make the discriminant large, but then it's hard to get your hands on these moduli spaces, like especially for general type surfaces. So, you know, it could be that, you know, one has to be a little bit cautious. But anyway, so these are the caveats. So now let me tell you what the theorem is. So the theorem says the following: suppose I have a smooth projective rational surface. So I have a rational surface here. H is a polarization such that H dot K is negative. Then if you look at the classes of the moduli stacks, then they stabilize in the completed Grothendieck ring, and they stabilize to something fairly simple. So they stabilize to 1 over 1 minus L to the minus I to the chi topological of X, a product of those things over all I, as delta tends to infinity. So that's the theorem. Maybe a few remarks. You know, this kind of condition, H dot Kx should be negative, is not such a serious condition if you're talking about things like P2 or the Alpezzo surface that's satisfied for every polarization. And on any rational surface, you can find a polarization that satisfies this property. But in general, it's a restriction on the polarization. So that's the theorem. So what are the consequences? The consequences is that first, the virtual Bettian Hodge numbers of these moduli spaces, again, here X is rational and H is a polarization that satisfies the same properties as the theorem. First of all, these stabilize, and you know what the generating functions for the stable numbers are. They are given by this. So you can actually work out what the stable numbers are. So in P2, you know, these things look like 1, 2, 6, 13, 57, to 29, 57, and so on and so forth. You can actually work these things out. And, you know, the other corollary is that suppose now you have a rational surface, H of polarization like this, and assume that there are no strictly semi-stable sheaves of rank R in first Chern class C. Like, then, you know, you can compute the Poincare and Hodge polynomials of these moduli spaces, and they do go to what you expect. So in particular, the tables that we saw in the beginning did not just look like they were stabilizing. They really do stabilize, and they stabilize to what we think they do. Okay, and the key point, of course, here is that this is independent of the rank, like we were expecting. All right, so that's the theorem. Maybe I should stop for a second and see whether there are any questions, and then maybe I'll say a few words about how you go about it.
So is the reason for this corollary is just that the moduli space and moduli stack are essentially the same?
They are essentially the same. I mean, I think one is a C star germ over the other one or something like that, yeah. You see that it's not quite the same formula if you're asking why is this 1 minus T squared coming in, right? That's because, you know, the moduli space, you know, it's Yeah, I mean, that's the effect of the C star, yeah?
And another question, is this formula similar to the formula for abelian or K3 surface?
Is this formula similar to the formula for abelian or? Well, I mean, it is similar in the sense that, you know, what you do is you take Gottsche's formula, right? You multiply by 1 minus q and set q equal to 1. And that's the formula that you get. I mean, the conjecture is that that should work no matter what the surface is. And the statements are is that that really works for K3 surfaces and rational surfaces if you make the enough caveats.
So maybe I missed. Do you really mean that for arbitrary surface, it should only depend on its topological Euler characteristic?
Oh, you're asking whether it should only depend on the topological Euler characteristic? No, that's not what I'm saying.
Okay, that makes sense.
Right. The point is that then this thing simplifies for rational surfaces because you don't have B1 and B3 and things like this. You can simplify the expression a little bit. Okay. So maybe I'll just say a few words about how you can go about doing it in the last 10 minutes. So the way we do this thing is we use Joyce's wall crossing machinery. So here I put the formula. I'm not going to even explain what it means. I'll just say a few words. So the way you should think about it is that you want to study what happens to these moduli spaces as you vary the polarization. And as you vary the polarization, the way these things work is that you hit a wall. And at the wall, at the wall, some sheaves that were stable can become destabilized. And some sheaves that were not stable can start becoming stable. So the way that happens is that, you know, you have some Harder-Narasimhan filtration, right? And then, you know, the slopes of the factors, the reduced Hilbert polynomials factors can become equal and then switch signs depending on how you're crossing the wall. And then what Joyce does is that he tells you for the class of the moduli stack in terms, so the way you should look at this formula is that you have the moduli stack when the polarization is H1 and you have the moduli stack when the polarization is H2, and you should ignore this formula and pretend that L is equal to 1. So what this formula is saying is that the classes of these things are equal, but that's not quite true because, you know, when you cross some walls, some things became destabilized, some things became stable. And so what you have to do is you sort of have to add in and subtract what happened. But the way you should view this formula is that MH2, the class of MH2 is the same as the class of MH1 plus some corrections that happened as you crossed walls, okay? All right, so then you see the first thing that you need to show is that if you have two amples, or you can make one of them be big and F or something like this, right? Then actually, like, you know, if you have stabilization, like, you know, the point is that if you look at this Joyce formula, you know, under the appropriate assumptions and you've made your discriminant large enough, then actually the correction terms only affect things in high codimension. They don't affect low codimension things. There are correction terms, but, you know, they don't bother you too much. And then the point is that if you fix yourself in some compact part of the ample cone, then you can actually choose this, how big you need to make it independently of this, you know, independently of these ages, and you can just depend on this on this compact set. All right, so this is saying that, let me go back, you know, you have the Joyce formula that's telling you, you know, MH2 is the same as MH1 except for these correction factors, and like what you observe is that if the discriminant is large enough, then the correction factors like mess things up, but they mess it up in higher and higher codimension. Okay, so in particular, if one class stabilizes as you let delta tend to infinity, the other one doesn't. They have the same stabilization. Okay, so then so this is if you change the polarization, then the next thing that you have to do is you need to figure out what happens if you blow up the surface. So, you can make these series for the surface and for, the blow up of the surface. And then you get to choose different classes. Like you can write the pullback of C minus M times the exceptional curve if you have a blow up. And then the next thing that you need to say is that there is a relation between the blown up series and the original series. And, this relation is the blow up formula of Yoshioka and Moscovoi. And, this correction factor has some form. Again, it doesn't matter what these forms are, there's some work to show some of these things, but there's some relation. Okay, and then the thing that you need to do is you need to say that, okay, if the sequence stabilized, and like you want to say that what happens to the blow up in this ring and the original thing, and you need to show that the blow up, the classes for the blow up one stabilize if and only if the original one does, and then you need to find the relation between them. And the relation between them is, again, you study this formula. Again, I'm not going to belabor too much what you have to do with the formulas and stuff, but it gives you what you think it should give, which is the 1/1 minus L to the minus K multiply K1 to infinity. Okay, so what this is saying is that if you vary the polarization, what you expect happens, and if you blow up, what you expect happens. So now to do things for, this is, I don't think we need to know the proof. To conclude, you need to compute, the key point here is that the minimal rational surfaces are P2 and these Hirzebruch surfaces. And what you need to do is you need to figure out what they are for these and then blow up successively to get to an arbitrary rational surface. So what you do is so every rational surface can be obtained successively blowing up one of these surfaces, right? So what you do is you first have to understand the moduli spaces on F1. So that's the blow up of P2 at the point. And then the theorem there is that, it holds. So this is really the hardest part of the computation, so you have to do it. And the way you do it is that, if on F1 you look at, so if you look at this moduli stack with, I don't want to call it a polarization because it's not a polarization, but let me say, so to speak, polarization in quotes F, the fiber class on F1. That's of course not the polarization, but you can describe the moduli space of slope semi-stable things with respect to F. And in fact, Moscovoi did that more generally for ruled surfaces, and you can compute the class of that explicitly because there things look more or less like they are on a curve. All right, so once you have that, then you want to go all the way to the other edge of the Neff cone to the pullback of the hyperplane class from P2 and relate this moduli space to the one coming from sort of, I don't know, from the Neff class F. And you use all these Joyce machinery to do that, and then you can compute the moduli, the limit in that case. So that's what I'm saying is that you use Moscovoi's computation for this, and then you need to do all the wall crossing to come to here. The key point here is that when you do this calculation, you need to assume that the rank divides C.F. Otherwise, the stack is empty, so there isn't much to do. Okay. And once you've gotten to the class E plus F, now now you can use the blow-up formula to get the formula for P2. So now once you get it for P2, then you can go back and find the formula for F1 without any restrictions on R dividing C1.H. And once you've done that, then you are now essentially home free. You can get the ether Fe, the Hirsch surface Fe from Fe-1 by an elementary modification, so that you use up the blow-up formula twice to relate one to the other. And once you've gotten all the minimal ones, then you do the induction on the number of blow-ups together. And eventually you get the statement that I said in the beginning. So I think my time is almost up, so maybe I'll stop here and say thank you, and I can answer some questions if there are any.
Thank you, Izzet. Let's thank Izzet for nice talk. Any questions?
Do you expect the conjecture to be true for quasi-projective surfaces? And do you expect some kind of cut and paste relations? Like if you cut your surface into something open and something closed?
Possibly. I mean, I think that like somehow like there seems to be a phenomenon here that like, the numbers that one seems to get, like no matter what you do, if the discriminant tends to infinity, you always seem to end up with the same numbers for the same surface. Like even in cases that you don't, that are not so obviously related to this. Like if you look at moduli spaces of one-dimensional pure sheaves, right? Even in that case, I think the numbers are the same in the cases that we know. So it's possible that there is a much more general story here, but I don't know any results for quasi-projective surfaces. So, I mean, it's possible that something deeper is going on that we don't understand, but I don't know. It's a good question.
Izzet, I have a small question. Does your proof work for irrational ruled surfaces? It's a lot of things similar.
Yeah, it's possible that you could make it work, but we didn't do it. So I think the tricky part is, yes.
If you do it for the product and then using elementary transformation, you repeat the last part.
Right. I mean, it probably can be made to work. Some steps probably, like, there are some cheats that we did that we shouldn't have done that you would have to work around. But you probably irrational ruled surface, I wouldn't be too surprised if you could get it. I mean, because as I said, the Moscovoy formula works for more generally. You don't need it to be irrational. Like, it works for irrational ruled surfaces as well.
And basically it means Kader dimension negative, so it's kind of looks better. Looks better,
yeah.
Any more questions? Okay, if there are no more questions, let's thank Izzet again. Thank you very much.
Thank you.
Thank you. Thank you, and okay, see you next Thursday, on this coming Thursday on ZAG.
All right, thanks.
Thank you very much. Thanks.
Bye.
Thanks.
Bye.